So now let's do a little bit more practical but more complicated example. It has some interesting twists to it. We're going to estimate the cube root of 30 using a Taylor polynomial with 6 terms centered at a equals 27. So just like in linear approximation, we use a equals 27 because you know what the cube root of 27 is. It's 3. But I don't know what the cube root of 30 is, so I'm going to use what I know to estimate what I don't know. All right, so here it goes. I need to know f of 27 and f prime of 27 and f double prime of 27. And it says 6 terms, so we have to go up to f5. F triple prime of 27, so this is sometimes called the 5th degree Taylor approximation. F4 of 27 and f5 of 27. All right, so to figure out what these things are, like some of them are easy. F of 27 is cube root of 27, which is 3, so that's easy. All right, but the rest of them, I need to know what f prime is to start with. So since I need to do a derivative, let's write the f of x as x to the 1/3 because it's cube root. All right, and then I'm just going to list all the derivatives down here. So the first derivative is 1/3 x to the negative 2/3. Then we're going to have, so now it gets a little complicated, right? Because you got to do, it's just power rule, but negative 2/9 x to the negative 5/3. And then if I do negative 5/3 times negative 2/9, I get 10/27. And that's x to the negative 8/3. And then multiplying again, it's going to be negative 80 on the top. It's going to be 81 on the bottom. And that's x to the negative 11/3. And then multiplying again, I get 880 240/3 x to the negative 14/3. So it's, some interesting patterns. You notice the numerator here is going down by 3 every time. The denominator here is just powers of 3, right? 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th. However, the numerator is a little tricky to get a handle on. It's hard to write an expression for. Fortunately, we don't have to. It's not impossible to write an expression for it. And it is not difficult to write a computer program to do it either. But to write a mathematical expression that is explicit is difficult because this is really recursive process. All right, so when I do f prime of 27, so that's going to be 1/3 times 27 to the 2/3 power, right? Because the negative 2/3 is going to put the 27 to 2/3 in the bottom. So that looks tricky to figure out, but it's really not, because you're doing the 2/3 power means I'm going to do the cube root and then square it. So the cube root of 27 is 3. I know that. So I'm going to have 3 squared times 3, which is going to give me just 3 to the 3rd power. So this one is going to be 1/3 to the 3rd power. And I'm going to get the cat out of here. Hang on. Yeah. Okay, so then the next one is going to be, I'm going to have this fraction negative 2/9. So let's just put the 2 in the numerator and the 9 in the denominator. And then I have 27 to the 5/3. And again, that sounds like something weird to do, but it's actually not, because your numerator is 2, but then think about the denominator, because the cube root of 27 is 3 again, and then we have 3 to the 5th power. And then here you have 3 to the 2nd power, 3 squared. So what I really have in the denominator is 3 to the 2nd times 3 to the 5th, which is 3 to the 7th power. All right, and then you can keep doing that. So my next one is going to be 10/27. So I have 10 in the numerator, 27 in the denominator, and then I have times 27 to the 8/3 power. So again, 27 to the 8/3 is just going to give me 3 to the 8th, and 27 is 3 to the 3rd. So I just add the exponents to get 3 to the 11th. So I have 10/3 to the 11th. And then for my next one, just following the same pattern, I'm going to have negative 80 over 81. That's coming from here. And then I have x to the negative 11/3. So it's going to be times 27 to the 11/3 power. Come on, cat. He thinks it's not math time. So I'm going to have 3 to the 4th here and 3 to the 11th here. So it's going to be 3 to the 4th. And 3 to the 11th. Yeah, it's going to be 3 to the 15th power. So this is negative 80 over 3 to the 15th power. And then my last one is going to be 880 over, now this 243 is 3 to the 5th power, so let's just write it that way. And then I'm going to have 27 to the 14/3. So I'm going to have my numerator is 880, and my denominator is 3 to the 5th times 3 to the 14th, so that's 3 to the 19th power. So a cool thing happens here, which is that the denominators are going up by 4 powers of 3, right? 3 to the 3rd, 3 to the 7th, 3 to the 11th, 3 to the 15th, 3 to the 19th. But then the numerators are a little bit hard to track, and there's no nice explicit formula for it, but you can write a nice recursive computer program to get it. All right, so then the next thing you're going to do is say, I need my coefficients to go over n factorial. So one thing that I decided to do, because I have to put this fraction over n factorial, so let's do our usual shortcut for doing that. Instead of writing 3 over 0 factorial, I'm going to do 3 times 1 over 0 factorial. Right, so then I'm going to make this 1 over 3 cubed times 1 over 1 factorial. Right, just instead of dividing by the factorial, I'm multiplying by the fraction. And then let's go ahead and combine them together right away. So this is going to be times 1 over 2 factorial. So let's make it minus 2 over 3 to the 7th times 2 factorial. And then this one will make it 10 over 3 to the 11th times 3 factorial. And this one is negative 80 over 3 to the 15th times 4 factorial. And then this one's going to be 880 over 3 to the 19th times 5 factorial. So it looks like a big mess, but you're going to see a lot of neat simplifications are going to happen out of this. And then you want to remember that these are the coefficients. So our terms that we're multiplying the coefficients by are x minus 27 to the 0 power, x minus 27 to the first power, x minus 27 to the second power, x minus 27 to the third power, x minus 27 to the fourth power, and x minus 27 to the fifth power. All right, but before we start plugging all that in, let's think about the fact that we're trying to find the cube root of 30. So that means we're going to use x equals 30 for all of these. We're all going to use x equals 30. So what's nice is these things are all just 3. All right, so let's see what we can put together. What we're going to write is now a Taylor polynomial because we're only writing finitely many terms. If it was all the terms, we'd call it a Taylor series. Also, since it's the Taylor polynomial with 5 as its highest power of x, we usually call it T5, the 5th Taylor polynomial. All right, so what I'm going to have is 3. This one's just going to be 3, right? So 3 times x minus 27, 30 minus 27 to the 0 power. So 3 minus, 30 minus 27 to the 0 power is just 1. So this one's just going to be 3. And then your next one is going to be 1 over 3 cubed times the 1 factorial we'll forget about because they're all 1s. So I'm going to have 30 minus 27 to the first power. So I'm putting 30 in for the x's now. And then I'm going to have minus 2 over 3 to the 7th power times 2 factorial times 30 minus 27 squared. And then I'm going to have plus 10 over 3 to the 11th power times 3 factorial times 30 minus 27 cubed. And then my next term is going to be minus 80 over 3 to the 15th power times 30 minus 27 to the 4th power. And then I have my last term plus 880 over 3 to the 19th times 5 factorial. I left off my 4 factorial here. There's a 4 factorial in there, right? That one. Okay, so then that 880 over 3 to the 19th power times 5 factorial times 30 minus 27 to the 5th power. All right, now I've not taken advantage of the fact that I know what 30 minus 27 is. So I would like to take advantage of that fact, but I'm watching the clock here. These videos don't upload well if they get longer than 10 minutes, so I'm going to break this and we're going to look at how this falls out in the next video.